Okay, for the third recording here, we're going to talk about the second discussion board, cognitive neuroscience. You guys did a nice job of defining it, and you can just write down a definition from one of your posts. But basically, cognitive neuroscience is where you take cognitive phenomenon and try to find out their underlying neurobiological roots. There's a lot of what we call type reductionism going on here, where when you memorize things, is this what's going on in your brain? When you're having memories or emotions, is this what's going on in your brain as well? And I want to go through a few examples with you on this situation on cognitive neuroscience. So for the first studies I want to talk about, and we'll get back to long-term potentiation a little bit later, is research reported in your book, not very well reported in your book, but I'll bring it out to you here, by Joe Ledoux, who's been doing this research for a long time. So I kind of wanted to give you kind of the baseline of what happens in his experiments here. Kind of three trials that we have going on here. In trial one, you basically take a rat, you put him in a Skinner box, and you turn on a tone. And you basically find that when you turn on the tone, nothing really happens. The rat just sits there in the Skinner box and nothing really occurs. In phase two, instead of just turning on the tone, first you turn on the tone, but then after you turn on the tone, of course, what do animal psychologists like to do? They have the grid set up, the place where the rat is standing, with electrical shock. So they shock the grid. The rat basically jumps up, and then when it lands, it'll have a freezing response, like, what the heck was that? And it'll also have an increase in heart rate and blood pressure. So that happens in phase two. And then most importantly is what happens in trial or phase three. In trial three, you just turn on the tone, and all of a sudden the rat goes into this freezing response and this increase in heart rate and blood pressure. And this is called a conditioned emotional response, how we can be conditioned by something to have an emotional response. And on trial three, only the tone is turned on, but something must have happened during trial two. And so if you're in the field of cognitive neuroscience, you try to trace this back, and what they've basically come up with is the key structure in the brain that seems to control emotions is the central nucleus of the amygdala. And what they've done in follow-up trials is when they cut the connection between the amygdala and the hypothalamus. Remember, the hypothalamus controls the pituitary and the adrenal glands and so forth. And when they cut that area, you no longer see this increased heart rate and blood pressure going on. And so that's very type reductionistic, and the idea of you block this connection and you lose that part of the emotional response. The freezing response, and you'll have to look up the spelling of this in your book, they've also traced from the amygdala, despite all the things shown here, to the periaqueductal gray. That's where all the endorphins are housed. It's called the periaqueductal gray. And what they basically find is when you cut that connection off, the freezing response is lost. So this has led Ledoux and other researchers to come up with this idea that the hypothalamus and the periaqueductal gray are very involved in conditioned emotional responses, where you learn something at one point, but then even when it doesn't exist, these things happen because the amygdala is the key emotion center of the brain, the central nucleus especially, the basolateral nucleus, if you will, and that controls emotional behavior. So method, result, and finding from there. Okay, well, that didn't take too long. Next, page 414 of your book, Candela and Sea Slugs. They don't do a very good job of describing this in your book, but kind of let me give you the Reader's Digest condensed version of things. What they basically do is, in a sea slug, you have many different areas of the sea slug, as you can see on 414, and they basically will take the mantle shelf and they'll shock it. And when you start shocking it, at first you'll see the gill withdrawal reflex be very, very strong. It's sensing fear, and the gill will withdraw. If you start doing this over and over again, you'll basically find that the animal will kind of habituate to this. It won't really have the major gill withdrawal response. So that's stage number 1. In stage number 2, what you do is you go into the mantle shelf again, and this time you deliver a really strong shock to that area. Just one shock to that area, and you'll see basically a huge gill withdrawal response. So that's called sensitization. What's most interesting, though, is what happens after this one shock in stage 2. In stage 3, they'll just give a weak electrical shock to the mantle shelf, and they'll basically find a huge gill withdrawal response. So once again, the idea is that what is going on between phases 2 and 3 in a type reductionistic way, again, it seems as if something must have gotten interconnected, and your book talks about this. There seems to be an interneuron that releases serotonin onto this interneuron, and that leads to this strong gill withdrawal response for stage 3 of the trial. So once again, this is cognitive neuroscience trying to find type reductionistic links between what's going on in a sea slug, a very simple organism, and why you're getting these responses. And finally, last but not least, and this one might take a little more time, but that's okay, long-term potentiation. I told you to look up. Let me give you kind of the inside scoop of this. You guys had some good information there, but let me kind of give you the answer here. Once again, a 3-stage process here. Page 415 of your book kind of goes into it. I'm going to be very simplified about it, and that's what you should know. They basically take rats, and they take slices from the rat's hippocampus, and they put them in petri dishes. And they soak them in there, and then they do a little electrophysiological things. They deliver a small electrical stimulation presynaptically into what's called the perforant pathway, which I think your book has in it, and then they measure the electricity postsynaptically at CA3 in the hippocampus. And by the way, CA3, CA stands for cornu mons, which is the word for seahorse in Latin. If you're in neuroanatomy, you have nothing to do with your time, so this is what you come up with. So if you deliver just a small amount of electricity presynaptically, you'll get a small amount postsynaptically. Phase 1, just to these slices, not actually from the animal. In phase 2, what they actually do with these slices is they deliver high frequency tetanic stimulation. So they put all sorts of major electricity into the area of the perforant pathway and do what's called tetanic stimulation of these areas. And they find when you put all of the electricity in presynaptically, the postsynaptically at CA3, you'll find a huge EPSP, a huge excitatory postsynaptic response that'll lead to, more action potentials going on. But what's really interesting about this trial is what happens in stage 3. In stage 3, you could go in 1 to 4 days later and just deliver one single pulse, a simple electrical stimulation presynaptically. And if you do this up to 4 days later, it seems you get this whole big postsynaptic EPSP response. This is what is called long-term potentiation. It's an electrophysiological phenomenon where when you deliver tetanic stimulation in phase 2, in phase 3, if you just put a single pulse in there, then the idea is that will lead to a huge response. And the reason people are so excited about this in both cognition and cognitive neuroscience, they think this might be what happens when you remember long-term information. And let me kind of give you a little bit of a cognitive analogy of this. So let's say you're studying for a test, and let's say you're cramming. You're basically bombarding your brain with all this information at a cognitive level, studying hours and hours. Then you get to the test, you get a simple question, and you're hoping all this information will come out. The idea is, the analogy is, that maybe the bombarding of your brain in terms of trying to learn all this information, maybe that's like phase 2 tetanic stimulation. And maybe phase 3, when you have the single question on the test, maybe that's the single pulse that, if you're able to recall it, leads to all the memories and all the EPSPs happening in your brain. So that's why people are so excited about this. But let me give you a few weaknesses as well. Some people feel like the cognitive scientist knows about human memory, doesn't know anything about the brain, and they know this is how we memorize information. There's no doubt about that. But they say, oh, the cognitive neuroscience says this might be what happens when we memorize information, LTP. The cognitive neuroscientist knows a whole lot about the brain and this phenomenon of LTP, which is real, but doesn't know much about memory. And so, we kind of have two disciplines where they don't know really very much about each other, and they're basically making analogies here, saying, here's how we memorize information. Some people feel that this is a little premature because this is just working with hippocampal slices. Not that much has been demonstrated in animal studies with this destroying memory, and the analogy may not work for humans. You can memorize things many times for many days. Does tetanic stimulation really work when you're cramming for a test? So there are critics of this approach. We don't doubt that we memorize information by studying hard and then recalling it. We don't doubt that the electrophysiological phenomenon does happen, but whether or not this is what accounts for how we actually memorize information into long-term memory is an open question. So hopefully that answers that for you. Thank you very much. That'll conclude this presentation.